So we're going to just pick up where we left off in the last video. So we're going to talk about, okay, sometimes the solids of revolution that we are talking about don't have fully solid interiors. And so what that means is basically you have, instead of there being the area all the way down to the x-axis, there's actually an area that is between two different functions. So we've looked at area between curves already. There's some space that when you rotate that space, you're going to create a hole in the middle of it. All right, and it's hard to visualize sometimes. So if you have access to some form of a calculus textbook that has pictures for you that are generated by a computer, it's pretty easy to see. Or even if you just go to the Google search engine and ask for volumes of revolution images, and it'll show you them in a little nicer fashion than I'm able to. But to find the volume, if you have an area that's between two functions as opposed to just between a function and the x-axis, we use the exact same reasoning as before, but we imagine that the top function, the bigger of the two functions, goes all the way around, and we find its volume, and then we find the volume of the smaller one and we subtract them. Okay, so in other words, we take the whole out by taking away the g of x, the smaller of the two functions. And so what you end up with is a formula that looks very similar to what we were doing before. It's just f of x squared minus g of x squared, where f of x is the top function. We've talked about that in the area between curves video, and g of x is the bottom function. So it's a very easy formula to use. You just have to, again, figure out what is the top function, what is the bottom function, and does it stay consistent all the way through. And it has to, or otherwise you have to switch your integral somehow. Okay? Show you an example of that. Here's an example where you have, it says page 472 of the textbook. If you have that, our particular textbook, if you don't, then it's fine. You will still see f of x is given to you, and it's x squared plus 1/2. That's what it tells you that one is. And then g of x is x. All right, and it tells you to go from 0 to 2. So when you look at this shape, you can see that the x squared plus 1/2 is the top function. It's above x the whole time. And so our volume, to find the volume of this, because it gives us the intersection points, they don't actually intersect. The two functions actually never intersect, but it tells you start at 0 and go to 2. Then your volume formula just becomes the 0 to 2 go on your integration limits. So your lower limit is 0, your upper limit is 2. And then your top function is x squared plus 1/2, and your bottom function is x. And so you go f of x in terms of, what we're doing, it's f of x squared minus g of x squared. So this is our f of x, and this is our g of x. All right, that's f of x, that's g of x. And then you just integrate that, but this doesn't integrate right away because we don't have a chain rule for integration, so we have to expand it first. So if we expand that, we square this, we get x to the 4th, we square 1/2, we get 1/4, and then we multiply these together to get half x squared and double it. So it gives me x squared. And then that x squared cancels with that one. So I just have the integral from 0 to 2 of x to the 4th plus 1/4. I integrate that, it gives me x to the 5th over 5 plus 1/4 x, and I'm going from 0 to 2. So if I plug in 0, it's going to go away, and if I plug in 2, I get 32 over 5 plus 1/2. All right, and if you add those together, you get a common denominator of 10. So you get 64 plus 5, and that gives you 69 pi over 10. And we're leaving it in terms of pi because that's the exact answer. If you integrate with your calculator, which you may, you can integrate this part, leave the pi out, and just integrate that part with your calculator, and it will tell you it's 69 over 10 or 6.9, and then you can add the pi in after. All right, so that's the concept of washers. That is when there's a hole in the function. Okay, here's another example, and again, for those of you that don't have the textbook but are watching the video, it gives you y equals root x, y equals 2, x equals 0, and it says do around the y-axis. So we've done a couple of examples where we've gone around the x-axis, and when we go around the x-axis, everything is in terms of x. But when it asks you to go around the y-axis with these, now everything's in terms of y. Okay, so we have y equals 2, that's our top function. And we have y equals root x, that's our bottom function. So usually what we're used to doing is going this way, right? We're going vertically. And if we were going around the x-axis, that is what we would do. But because we're going around the y-axis, now we're talking horizontal instead. So we're talking front function and back function, okay? But we have to write everything in terms of x equals something, and then our boundaries become in terms of y. So when y is equal to root x, that means that x is equal to y squared, okay? So our volume formula is going to be the front function is y equals root x. So when we write it as we have in terms of x equals, we have y squared, that's the front, and then minus the back function is x equals 0. So in a sense, we don't really have a back function because it's the y-axis. So we just have to do f of y squared minus g of y squared, that's 0, and this is y squared, right? F of y is. So we end up with this. And then that becomes the integral of y to the fourth. The integral of y to the fourth is y to the fifth over 5, and then you plug in 5 and you plug in 0. 0 gives you 0, so you end up with 32 pi over 5. So if you understand conceptually what we're doing in terms of going around the y-axis, it's horizontal, then everything is in terms of y. The boundaries are what the y values are, and the functions are x equals something with y in it, so that the integrand is all with respect to y. Okay? So it's a fairly simple process. I'll show you a couple of IB questions to go along with this, just so you can kind of see what they are looking for. All right. So here's a question. It gives you a function. It says y is equal to e to the x over 2. And then it says you're going to go from point P to point ln 2. And it says, first of all, to find out what's the coordinate of the point P, where the graph meets the y-axis. So we're going to say, if it meets the y-axis, then e to the x over 2 is our function, and x becomes 0, because we don't know where it meets the y-axis, which is where x is 0. So we get y is equal to e to the 0, which is 1. So the point P is 0 and 1. Okay. Now it says the shaded region between the graph of the x-axis, bounded by x equals 0 and x equals ln 2, is rotated 360 degrees above the x-axis. Write down an integral which represents the value of the solid obtained. So we're going to go with our pi integral from the lower boundary, which is 0, to the upper boundary, which it tells us is ln 2. Right? So we're going from 0 to ln 2 of the function squared. So e to the x over 2 squared. If you multiply x over 2 by 2, you get just e to the x. If you integrate e to the x, it stays as e to the x. So you're going from 0 to ln 2. And then you go e to the ln 2 minus e to the 0, because you're just plugging in the boundaries. E to ln 2 is 2, because you're raising e to the power. You have to raise e2 to get 2, if that makes sense. If you're not sure, you can type that into your calculator and it will tell you. And then e to the 0, as with any base, any numerical base raised to the 0, you get 1. So you end up with pi, and that's what it asked you to do. It asked you to show that that was pi. So we did that. So we're done. So that's the kind of question you're going to be asked to do. Here's another example. This one is another IB question, fairly simple. But it says the shaded region in the diagram is bounded by root x, x equals a, and the x-axis. So it tells you this boundary, but it doesn't actually tell you what it is. It just gives it a parameter, a. And it says when you rotate and get an answer, the answer comes out to this. So the volume is 0.845 pi. So we have to try to find the volume with our formula. So our formula is pi integral from 0 to a of root x squared, because f of x is root x. Square that, you get x. If you integrate, then you get x squared over 2 from a to 0. And when you plug in, you get a squared over 2 times pi, because it's minus 0. We don't write that. Then it says to find the value of a. So what we do is we say we know the volume is this. it's a squared pi over 2, it's also 0.845 pi. All right, so what I've done is essentially there's a pi there and there's a pi here, and I just cross them out. So I get a squared over 2 is 0.845. If you multiply by 2, you get a squared to be 1.69, which means a is 1.3. And that's your answer. Okay, so that's just another IB kind of level question to show you what those look like. And then we'll just do, I think do we have time? Yeah, we have time for the final one. The final one says, we're going to integrate this. G of x is this function, root 3 sine x cosine x to the 1/2, from 0 to pi over 2, and I want to find the volume generated when the curve of g is revolved through 2 pi about the x-axis. So this is our function, so we're going to square that, and we're going to multiply by pi, and we're going from 0 to pi over 2. So if I square this, root 3 squared is 3, sine becomes sine squared, and cosine x to the 1/2 just becomes cosine x. So I end up with a volume that looks like this. And then to integrate this, we have to use substitution. So we have to let u equal sine x, du equal cosine x, and then if u is sine x, the sine of 0 is 0, and the sine of pi over 2 is 1. And so we end up with u squared from 0 to 1. We integrate, we get u cubed over 3. The 3's cancel, and I'm going from 0 to 1. If I plug in 1, I get 1 cubed over 3. Or 1/3, that's where that came from, excuse me. And then if I plug in 0, I get 0, so that doesn't need to be there. And so my answer is pi. So that kind of gives you the level of question difficulty from IB, which you will notice is not that high. But we'll do some more questions out of the textbook as well. But that's the concept of finding a volume of revolution with disks and washers.